Welcome to section 14.2, double integrals and volumes. In this section we'll talk about Riemann sums and correlate it to what we saw in previous calculus classes with functions of one variable, and then we'll see how double integrals can be used to find volumes as well as the average value of a function. Also, we'll talk about properties of double integrals, and again it's very strongly connected to properties of single integrals that we've studied in the past. So the idea behind integrals is this notion of taking the limit of a certain number of volumes. So we can make a grid in a certain region, and then using the grid with little squares here, find the volume of each of the prisms that rise from the given square. And if we add the volume of all of these prisms, we get an approximation of the actual volume. In this case, it looks like an octant of a sphere. Now, if you take the limit as the squares or rectangles become infinitely small, then you get an integral and you get the exact volume of below the surface. Notice that it's not quite enough to have infinitely many of these grids. You need each of the grids, each of the squares or rectangles in the grid to become infinitely small. Having infinitely many could still allow some of them to not be infinitely small, and then, as you can see with all the examples here, it would be an approximate volume, not the exact volume. So just like we had MRAM, RRAM, LRAM in AP Calculus AB, we can use approximations to find volumes, and this is an example that treats this. So here we have Earth. It's kind of a slice of a hill maybe, and the depth of the Earth is given for the center of each squared. So we have this 10 by 10 squared, which has a height of Earth above it measured right in the middle of the square, that is 4. And then this square here has a height of 5 and then 3. And if we go closer to the y-axis, these are the places where the Earth is the deepest, and it's indeed 10. So these values here are measured at the center of each squared. So if we add the volume of what we would get as prisms, we get an approximation of the total amount of Earth in this region. So for each prism we do base times height, or length times depth times height. And therefore, for each of them, there's 12 of them, it's 10 by 10, 10 times 10 times 10, plus 10 times 10 times 9, plus 10 times 10 times 7, etc. 10 times 10 comes from the fact that the squares are 10 meter long, and the height is given here. So we add up all of those, and it ends up being 7,000 cubic meters of Earth. So this would be the definition of the double integral. It's the limit as the areas approach 0. So, properties of double integrals. We will go over the 5 of them and see how they correlate to properties of single integrals that we have seen in the past. Number 1 is very similar to what we've seen in the past. So if you multiply a function by a constant c, then its integral will be also multiplied by the same value c. That is a straightforward extension of what we've seen before. Likewise, number 2, if you have two functions, then you can integrate each function separately and add them later. So this is what we do all the time without even realizing. If I'm integrating x squared plus 2x, then I'm integrating x squared, and plus I'm integrating 2x. Number 3, if a function is greater than 0 for all the points x, y in the given region, then the integral will be positive. This corresponds to the area under a curve being positive if a function is always positive, a function of one variable. So there's this similar thing that a double integral will be positive when a function is above the xy plane, and the double integral would yield a negative value if the surface is below the xy plane. Number 4, if a function f is higher than a function g for all points in the region, which is shown here, f is higher than g for every point in the region, then the double integral of f is going to be greater or equal to the double integral of g. And if we remove the equal, then the equal would also be removed here. Finally, number 5, the double integral over a region of a certain function can be split into two double integrals over two regions R1 and R2 if R1 and R2 together form R. They need to be, if the union needs to be R, and it needs to be not overlapping. This is what we used to see in AP Calculus AB as this one here. The integral from A to C is equal to the integral from A to B plus the integral from B to C. Here we split the interval AC into two subintervals that entirely covered AC without overlapping, and it's the same here with regions. So a sketch is shown here. Region R is this whole shape here, and then we can cut it through in the middle, and then we have R1 on the left, R2 on the right, so you can integrate separately on these two regions, and you'll get the same value as the integral on the entire region. So, example, evaluate the double integral on the region R given by x between 0 and 1 and y between 0 and 1. This will yield the volume under the surface of the function z equals 1 minus 1/2 x squared minus 1/2 y squared. In the previous section, we saw that the double integral yields the area of the region, and now I'm saying that the double integral is going to give me the volume. So what is the difference? The difference was that in the previous section, when we were finding areas of regions, it was the double integral of 1 times dA, or 1 time dx dy. Here, it's the double integral of a certain function f of xy, which is not 1, over the region. And notice that if f of xy, if the function we are integrating is equal to 1, it's a constant, it's a plane at height z equals 1, then the double integral over that region of 1 times dA will give both the volume under the surface as well as the area of the region. Because if it has height 1 everywhere, then the base times height is going to be equal to the base. So pay attention to, if there is nothing here, then you're finding the area of the region. If there's something, then you're finding the volume under the surface. Alright, so here's the representation of the surface, and we are integrating on a square, which is not very square here, but we are integrating on a side 1 square. So we integrate from 0 to 1 and from 0 to 1. The limits of integration were given right there, and all these steps from here on are pretty easy. Instead of integrating in the order dy dx, it's perfectly fine to integrate in the order dx dy, and there's no complication here. This is an arbitrary choice. So integration, I don't think is really challenging. We reach eventually the answer that the volume under the surface here is 2/3. Find the volume of the solid region R bounded by the surfaces f of xy equals e to the negative x squared. Again, something that is not easily integratable. And the plane z equals 0, y equals 0, y equals x, x equals 1. So region here is not great. Region we have been talking about that word every time until now by meaning the region in the domain. So it would be this triangle here. Here, somehow the solid region is the actual volume. So be careful. Okay, so first we need to define what the domain is. And if we have the support of a sketch like we do here, we notice that it is a triangle bounded by y equals 0, by x equals 1, and by y equals x. So we need to choose the order of integration. It could be dx dy, it could be dy dx. If we decide that we want to try dx dy, then we need to look at y first, and y ranges from 0 to 1. And then for any of these values of y in the middle, we see that x ranges from x equals y to x equals 1. So if we pick a certain value y here, then we integrate from x equals y to x equals 1. So y goes from 0 to 1, and then goes from x equals y to x equals 1 of this function. If, on the other hand, we decide that we want to integrate in the order dy dx, then we need to look at x first. X ranges from 0 to 1, and then if I pick a certain x here, then y will go from 0 all the way to y equals x. So this is why the limits of the integral are x equals 0, x equals 1, and y equals 0, y equals x. Now we have two possibilities, but just like last time, we have one that is recognized as impossible to integrate. E to the negative x squared dx cannot be integrated. However, this one is going to work. If we integrate in terms of y first, then the integral is y e to the negative x squared. We substitute, and it allows us with a little u sub here, maybe u equals negative x squared if you want. The other way is to just see that the integral is going to be this, and eventually you get to the volume equal to 1/2 minus 1 over 2e. Average value of a function. In APCalc-AB, we remember that the average value of a function is the integral of the function divided by the length of the interval. In multivariable, if we have a function of 2 variables, then it's very, very similar. It's the double integral, but then we have to divide by the area of the region we're integrating on. So just like the interval was here, we have the area, or the length of the interval is replaced by the area of the region. So, quick exercise, what is the average value of the function that we just discussed above on the region defined? So, the average value of this surface here means how high am I going on average? Right here, the height is 1. Right here, the height is a lot smaller. So on average, how high is the function? And if we proceed to calculating, we have already calculated the integral, so that's easy. We got the answer just above, 1/2 minus 1 over 2e. All we need is to multiply by 1 over the area of the region, which is, this should be 1 over a, and since the area of the region is 1/2, it becomes 2 times the integral that we found. So negative 1 over e plus 1. Wallace's formulas. There are 2 formulas that are gonna show up once in a while in the next few weeks. We don't have to memorize them, but they can be useful, and they give us the integrals of powers of cosine in very specific cases if we integrate from 0 to pi over 2. If we have an odd power, like n equals 5, then the integral from 0 to pi over 2 of cosine to the 5th power of x dx is going to be given by this expression, and it depends on the value of n. If we chose n equals 5, then the integral is 2 over 3 times 4 over 5. If n equals 7, then it's 2 over 3 times 4 over 5 times 6 over 7. So we go up to n at the denominator. If we have an even power of cosine, then this is the rule. The integral would be 1 over 2 times 3 over 4, etc., times pi over 2. Notice the difference here. There's a times pi over 2 that is always included no matter what n is. So the integral from 0 to pi over 2 of cosine squared x dx is 1 over 2 times pi over 2, which is pi over 4. So keep this in mind when you have an integral of a cosine. It's going to be useful a few times in the near future. Here we have one of the longest and most complex in terms of number of steps, exercises of all the notes we've done all semester. Find the volume of the solid region R bounded above by the paraboloid z equals 1 minus x squared minus y squared, and below by the plane z equals 1 minus y. So we have a plane, we have a paraboloid, and between them they form a certain volume in space, and we wonder, what is that volume? How big is that region in 3D? So first we need to find the region R in the domain. So this is basically what we're going to use for defining the limits of our integration. And so in order to do that, we need to find where these two surfaces intersect. So we set up one equal the other. We get 1 minus x squared minus y squared equals 1 minus y. And if we clean it up a little bit and use completion of the square, we get that it's actually a circle. X squared plus y minus 1 half y minus 1 half squared equals 1 over 4. So it's a circle centered at 0, 1 half. Okay, so to find the volume, we're going to have to find the double integral over the surface that is on top and subtract the volume for the surface that is below. So double integral of the paraboloid minus double integral of the plane over the region that we have just figured out, which is the circle. Here it is. So how are we going to define R? Well, if we go in the order dx, dy, then we can see from this little sketch that y ranges from 0 to 1. And then if I pick a certain value y along the range of y, then x ranges from the negative square root to the positive square root. From negative square root of 1 over 4 minus y minus 1 squared to positive square root of 1 over 4 minus y minus 1 squared. So once we have set up the two integrals separately, we can put them together by just using the property number 2 from above, and we get a double integral of negative x squared minus y squared plus y, and here we change our r with the specific values y equals 0, y equals 1, and etc. And then we have to integrate. So integrating this in terms of x is not very hard. You get that, and then we need to substitute the minus square root and plus square root. Now notice how this is always going to give us 2 times the square root, actually, because we're substituting square root and then minus negative square root, so it's always going to give us 2 times the square root. So the result is negative 1 over 3 times, this is a multiplication, 2 times 2 times the square root, minus, and then I substitute square root and minus square root, so minus y squared times 2 times the square root, plus y times 2 times the square root. Here we can factorize a square root. Notice that here we had the square root to the power of 3, so if we factorize one square root out, we will have a square root squared, so it will just vanish, which explains why we have this term here. And then you probably want to work this out yourself, but it makes complete sense that it ends up being that. And then if we distribute further, things continue to simplify. Also, inside the square root, 1 over 4 minus y minus 1 squared, it is possible to go back and distribute and get to this. In fact, this is a step we had earlier right here, y squared minus y, or y minus y squared. So from here to there is also very, very easy. You just have to expand and simplify. However, the step from here to there requires a little bit more explanation. How does this y minus y squared becomes 1 minus 2y minus 1 squared? This is one of the few crazy steps in this in this exercise. So let's look at it backwards. Rather, 1 minus 2y minus 1 squared. If we expand, we get 1 minus 4y squared minus 1 plus 4y, and this cancels out, and then we can factorize out 4. So we get y minus y squared equals this expression over 4, which is what we've done here. We have this expression that becomes, well, this expression over 4. And this divided by 4 can be pulled out as a fraction, 1 over 2. Same here, y minus y squared. We used what is shown in the little pop-up window to write this. And that the 1 over 4 cancelled out with the 4 up here, which explains why it's just 1 over 3. Second crazy step is a U substitution that who knows why someone ever thought that was a good idea. Maybe there was many attempts, maybe someone has crystal clear vision of what happens mathematically. Anyway, it's an unbelievably clever U substitution, or maybe theta substitution we should call it. The substitution is to decide to write 2y minus 1 as sine theta, or sine u if we wanted to call it a U sub. What that does is that now, if we take the derivative, 2 dy is going to be equal to cosine theta d theta. Why on earth would that help us? Well, if we do that, we get the integral. You can check that the limits of integration are indeed negative pi over 2 and pi over 2, but we have the square root of 1 minus sine squared theta. There's a little squared here. Times, again, here this is 1 minus sine squared, and you're gonna have to think for a little bit how all of these things work, but in the end we have 1 over 12. So there's a 1 over 6 and a 1 over 2 here. Through this amazing U substitution, we now realize that 1 minus sine squared is actually cosine squared, and with the square root it becomes cosine. 1 minus sine squared is cosine squared, and we had a cosine here, so all in all it's the integral from negative pi over 2 to pi over 2 of cosine to the 4th power. We have one more thing to do before we can apply, maybe you realize it now, Wallace's formula. We need to be aware that there's a symmetry about the y-axis. If I integrate cosine to the 4th power of theta, it's an even function, so instead of integrating from negative pi over 2 to positive pi over 2, I can integrate from 0 to pi over 2 and then double that value. So this explains why we double the value. It's 2 times 1 over 12 times this. Because 4 is an even power, we can apply Wallace, and here's what we get in the end. The volume that we were looking is pi over 32. This is the volume that we were looking for. It's you have the paraboloid and the plane, and we were looking for the volume of this tiny region here, and you can see pi over 32 is very small. It's just like a pimple on the surface of this plane. Well, that is it. This exercise is unusually complex, obviously, but I think it's interesting to see complex exercises in the notes. But then the number of steps is ridiculous, and the chances to make a mistake if you're solving it on your own is like 99%. It's just very hard, but the challenge of following these steps is what is valuable here. So thank you so much for listening.